Hello guys, so I would like us to look at Fourier series. So Fourier series basically involves expressing functions in some infinite form. Now, some definitions that we have, like periodic function. A function is said to be periodic if its function values repeat at regular intervals. So let's say, for example, we have a function like this. You see, after x1, it's repeating itself. So basically, that's what we call a periodic function. The regular intervals between repetitions, so the intervals between repetitions is what we call a period. Okay, let's look at an example. If we have an arbitrary sine function, if we are to draw the graph of y is equal to a sine nx, in particular, y is equal to sine x. So you come and plot the x and y values at x is equal to 0, sine of 0 is y. At x is equal to 90, you will get the value to be 1. At 180, you will get it to be 0. So coming to plot that all the way to 2 pi, this is how the curve is going to look like. If we were to continue, we will realize that from after 2 pi, the curve starts repeating itself. It takes the position, the same position it was in at 0, and it will just go on like that. So the distance from 0 to 2 pi, where it starts repeating itself, is what we call the period. And the displacement on the y-axis is what we call the amplitude. Generally, for any sine or cosine curve, y is equal to a sine nx, y is equal to a cos nx. The amplitude is given by a, and the period is given by 360 divided by n. So here our n is 1, clearly. So 360 divided by 1 will be 360. So that's why the period is 2 pi. And our amplitude is obviously also just 1. If we are to take up another example, so if we are to plot the curve of y is equal to 5 sine 2x, then it will look somewhat like this. So whereby the displacement on the y-axis will be 5. So obviously that will be our amplitude, and it will start repeating itself after pi. That is after 180 degrees. So our period will be 180. So clearly we said that period is equal to 360 divided by n. So 360 divided by our n here, as you can see, is 2. So our period is obviously 180 degrees and our amplitude is 5. Now, next definition, harmonics. A function f of x is sometimes expressed as a series of a number of different signed components. Now, the components with the largest period is the first harmonic, or the fundamental of f of x. Let's say, for example, we have y is equal to sine x, y is equal to a sine nx generally. So let's say we have y is equal to, so where the value of n is 1, okay, so where we have the value of, so let's say we have a1, then we have sine of x. Let's say we have a different value of y with a2, sine of 2x, and so on, all the way to sine nx. Now, clearly, the one that's going to have the largest period will obviously be this one, because this is basically 360 degrees divided by 1. This will be 360 degrees divided by 2 to get the period. So the period here will be 180, the period here will be 360 degrees. So this one here that has the largest period is what we call the first harmonic, or the fundamental harmonic. Now, non-sinusoidal periodic functions. Now, we've looked at the sinusoidal ones. The sinusoidal ones are basically the ones that have the form of a sine curve, like they curve like that. Now, one thing we need to note is that a function can be periodic. Yeah, it has the repetition without it necessarily having to be sinusoidal. So, for example, this function here, as you can see, it's periodic after, like we start here at 0. So as you can see, at 14, it starts as you can see, it starts repeating itself. So it does not really have to be sinusoidal in order for it to repeat itself. Actually, it starts repeating itself here at 18. You see, we start at 0, then we go up, down, then at 8 here, it's like we started at 0 again. So it started repeating itself. We go again, then again at 16, it starts repeating itself. So the period is basically the distance after which it starts repeating itself. So as we can see here, the period is 8. Okay, so it's non-sinusoidal, but it's still periodic. Another example, we have this. So as you can see, this function here, it starts over here at 0, then goes up, then down, then it starts repeating itself from here. So obviously, the period is going to be 6. Let's look at this last one here. So it starts at 0 here, then it goes up, then it goes that way. Then clearly, as we can see, so these values are not indicated. Let me just indicate them. This is 5, this is 3, this right here is 2, this right here is 8, this is 7, and this is 10. So clearly, as you can see, it starts from 0. Okay, then after this, like it starts repeating itself again at this position 5 here. It goes up again, then like this, then slants, then at this 10 here, it also starts repeating itself again. So this function is obviously periodic with a period of 5. Okay, so how do we go about analytically describing these functions, analytic description of a periodic function? Let's look at this, a function which is repeating itself. Now, if you want to describe this analytic function, we can be able to analytically describe it in so many ways. Now, let's first of all look at the distance from 0 to 4. Now, if we see at x is equal to 0 here, and x is equal to 4, this is a straight line. As you can see, the value of y is equal to a straight line. So let me call this 3. So between x is equal to 0 and x is equal to 4, y is equal to 3. Between x is equal to 4 and x is equal to, this is x is equal to 6. So why do I have this as 8 here? This is 6. Between x is equal to 4 to x is equal to 6, then we have the value of y as what? We have the value of y as 0. So basically, if we want to write this, we can be able to write it as f of x is equal to, so it is equal to 3, and this is between x value at 4 and at 0, and it is equal to 0. This is where the x value is in between 6 and 4. Okay, so that's how we go about analytically describing these periodic functions. Let's look at this other one. Now, clearly, as we can see, between 0, x is equal to 0 and x is equal to 2, we have a line. So between x is equal to 0 and x is equal to 2, we have a line. We have a line. So equation of a straight line is given by y is equal to mx plus c. So in order for us to be able to describe this correctly, then we need to find the equation of this line. So we are going to take the 2 points. At x is equal to 0, we have y also being equal to 0. So let's take that as our point 1. At x is equal to 2, we have our y being equal to 2 again. So in order for us to get the equation of a line, we're supposed to get change in y over change in x so that we get the gradient. So change in y over change in x will be equal to, so let's take 2 minus 0 over 2 minus 0. So that will give us 1 as the gradient. And if 1 is our gradient, let's replace y is equal to mx plus c. Now let's take two values. Let's take at point 22. At point 22, y is equal to, okay, so So, our C is equal to 0. So our C is equal to 0. And so the equation of a line between that period is going to be y is equal to, our m is 1. So y is equal to x is the equation of a line here. Okay, let's look at from x is equal to 2 to x is equal to 6, because that's also, so between x is equal to 2 to x is equal to 6. So what do we have in between here? We have a straight line. So we're going to just follow the same procedure, so that because it starts repeating itself at this particular point here, as you can see. So after this, then we can be able to define it. And so let's see, at x is equal to 2, we have the point 2, 2. At x is equal to 6, we have the point 6, 0. So getting y is equal to mx plus c, let's first of all start by getting the gradient. So the gradient is change in y over change in x. And this is going to be equal to change in y. So we can have 0 minus 2 over change in x, we can have 6 minus 2. So this will give us minus 2. So this will give us minus 2 over 4. And this will be minus a half. So minus a half is going to be our gradient. So let's get the y-intercept c. So let's take 0.22. So taking 0.22, y is 2 is equal to m, which is minus a half, multiplied by x, which is 2 plus c. So what's the value of our c? This and this will give minus 1 on the other side. So c is equal to 3. So we'll have the equation of our line, y is equal to mx plus c, being y is equal to minus a half x plus the value of our c is 3. Now let's come and write that down in the description. So analytically describing this, we have f of x is equal to, so between 0 and 2, so 0 and 2, we have the value of f of x being equal to an equation. So f of x is equal to x, because we said y is equal to x there. And then between 6, between 2 now and 6, so we have between 2 and 6, we have our f of x being equal to the equation minus a half x plus 3. Now, since we know the period, we can be able to indicate that down here as f of x plus, it starts repeating itself after 6. So the period is 6. So f of x plus x is basically equal to f of x. And similarly on the upper graph as well, the period here was, so it started repeating itself. As you can see, it started here at 0, then it started repeating itself here at 6. So we can write this as well as f of x plus 6 is equal to f of x, basically indicating after plus 6, then it starts repeating itself. That's it for analytic description of a periodic function. So you can be given this value here, and then you're being told to now draw it. So you just come and read from 0 to 2, you draw that, and then you come and draw this equation of a line. And from 2 to 6, you do the same, you come and draw. The same way, if we were given this description here and we were told to draw, we already know that it is periodic after 6. So from 0 to 4, we come and draw, and it is just 3, which is a straight line. So from 0 to 4, we just come and draw a straight line here. Then from 4 to 6, it is 0. Clearly, as you can see, from 4 to 6, it's just 0. Since it starts repeating itself from 6, so the other values will just keep on copy pasting the trend of that graph. So that's it.